So today we're going to focus on a little bit more of a deeper understanding with independent events. As we go through this material, there's going to be some things that you're going to need to take note of. So we're starting out with those ideas here first. And I guess I'd underline if right here. If events A and B are independent, then you can calculate the probability of A and B as the product of their probabilities. So that's one important idea. Now, kind of going along with that, you might remember from the other day we were working with sampling with replacement and without replacement. So sampling with replacement means you look at an item from your sample, you take a look at it, you put it back in your sample, mix it up, and you can draw again. On the flip side of things, sometimes you take a look at a sample and then put it aside and then take your next draw, keep on going. That type of sampling leads to dependent events, whereas if you're sampling with replacement, it leads to independent events. Calculations with dependent events become a little bit more challenging, so it's nice to have around this 5% rule. That is, if your sample size is less than 5% of the population, you can kind of treat them as if they're independent events, even though they're not. Last but not least, there's this one. Do you remember what C bar is? C is some event, it can be anything, it could be like rolling a 6 with a 6-sided die. What's C bar going to be? The complement. It's everything but C. So in my case, if I was rolling a 6 with a 6-sided die, C bar would be the event of not rolling a 6, rolling a 1, 2, 3, or 5 with your 6-sided die. So with those ideas as a background, let's work through some examples. And this first one's actually going to come from your handout for section 4.3. And it's finding the probability of a couple with 3 children having at least one of them as a girl. So I'll just write that out here. And we'll go through a bunch of things, try and pull in some of this stuff here. Find the probability that when a couple has 3 children, at least one of them is a girl. Well, it's kind of a blend between 4.2 and 4.3. You're going to see some of this material in 4.2 and in 4.3. So I'm kind of covering it now. A lot of it's just really working with the idea of independence. And there's a lot of implications for our calculations based on that. So let me start out by drawing a little number line and looking at kind of our sample space, the different events, different compound events of things that can happen. So this is going to be the number of girls. So you have 3 babies. How many girls could you have? What are the different possibilities when a couple has these 3 children? What could you have in terms of number of girls? 3. Anything else? 2. Anything else? And 1. And none. Yeah, that's important to remember the none. Now, if we want to look at the event that at least one of them is a girl, then let's take a look at that. Here we go. At least one of them is a girl. If I was going to circle that on this little number line, what should I be circling? That at least one of them is a girl. Yeah, 1, 2, and 3. So these are your choices. Now, if you were to calculate the probability of this directly, that is, probability of 1 or 2 or 3, it's really a cumbersome calculation. There's a lot going on. You'd have 3 different ways you could have just 1 girl, 3 different ways you could have 2 girls, and one way that you could have all girls. So there's a lot of different calculations and probabilities you have to deal with. It'd be a mess. But here's where we want to use the complementation rule. That's this part right here. So let's call this event C. C is the event of at least one girl. So can anyone describe to me, in this case, what C bar would mean? What does C bar mean in this context? Patty?
No girls?
Yeah, no girls, all boys. However you want to say it, but let's just call it all boys. And that event looks a little bit simpler to deal with, right? I mean, there's just only one thing going on here. They're all boys. So our strategy in calculating this probability is, instead of doing this, let's use the complementation rule. Let's do probability of at least one girl is 1 minus the probability of all boys. So that's our goal moving forward. Let's write that out. So probability of C equals 1 minus the probability of C bar. Now let me write out what C bar is going to mean for us in terms of probabilities. It's going to mean the probability of all boys, which I'll write out like this. Probability of a boy on the first one, and a boy on the second one, and a boy on the third one. Now we got to think a little bit about this probability. Now, if you have a boy with your first child, does that affect the probabilities you're giving a boy on the second child?
No.
How about the boy on the third child? So what can I say about these types of events? Yeah, thank you. These are independent events. Are independent events. And you can star that. I mean, that's gold here for this calculation. Because what that means is I can change this for 1 minus the probability of B1 times the probability of B2 times probability of B3. So I'm breaking this down from this big compound event down into a bunch of little simple events. Steven, help me out here. What's the probability of a boy on the first one?
50%.
Yeah. Let me call it 1/2. And on the second one?
50.
Yep. So overall, it's going to be 1 minus 1 over 2 cubed, which is 1 minus 1/8, or 7/8. So yay, there's our probability. Nice. There's two things that help this go. One was we used the complementation rule. Second thing was that we used the fact that these events are independent. Nate, anything unsettling about that one? Looking good? Okay, thank you. Appreciate the feedback. Anything else on this one? It's kind of a nice one to kind of ease into things a little bit. Let's move on to another one. This one's on your handout. And I'm not sure that there's too many people here that would remember this event, but certainly people who are old enough to understand it remember it. I remember being in school when this happened, and it was the Space Shuttle Challenger. So let me get that pulled up here. Space Shuttle Challenger had on it 7 astronauts, among them Christy McAuliffe, and she was a school teacher. She was chosen in this nationwide search. She got to go on the space shuttle. It was a big thing. And I can't imagine the trauma it would be to her class watching this and then seeing the space shuttle blow up. Wow. That's just, man. That's, that's just not right. All right.
I didn't mean to laugh.
Yeah.
There's been studies on it affected kids on the East Coast differently to the West Coast, because East Coast kids were awake and watched it happen in school.
Yeah.
And West Coast kids were asleep and didn't see it in person.
Interesting. Interesting. Now, NASA managers said that the odds of something going wrong were 1 in 100,000. And that sounded like kind of a suspiciously round, arbitrary number to Nobel Prize winning physicist Richard Feynman, who was tasked with trying to figure out what went wrong. 1 in 100,000, that seems pretty odd. You would have to do test flights every day for 300 years to see one failure. I mean, wow. So this should be really, really rare. Even the manufacturer thought the odds were about or the probability was 1 in 10,000 of a mission failure. But when he talked to the managers and not the managers, but the engineers, they said anywhere between 1 in 50 and 1 in 300. So it's a lot different than this. To give you a perspective on this 1 in 100,000, back in 1986 when this happened, there was about 46,000 people who died in car accidents on U.S. roads. But we drove a total of 1.8 trillion miles. So that means the odds of, going on a car ride and ending in disaster, if those were 1 in 100,000, then you could take a trip of about 400 miles. For comparison, things have gotten better. In 2015, that distance was up to 882 miles. So certainly we've gotten better about things. But let's get back to the shuttle. Now, I remember at the time, there was an article that came out in the New York Times talking about how the shuttle was dependent on these called criticality 1 parts. A criticality 1 part had to work with a probability of 99.99%. So, wow. Let's take a look at that in terms of 99.99%. What is that as a decimal? Yeah. So, kind of an easy one here, 0.9999. Of course, it would help if I had something that would write. Let's try this one, 9999. So that's pretty good. But then we get to the second part. What's the probability that all 750 criticality 1 parts work? So to have a successful mission, all of these parts need to work. So, all right, let's play around with that a little bit. So I need some notation here. I'm going to let C1 be the event that the first criticality 1 system functions or works. The first criticality 1 system works. But we got a lot of these parts, right? So we'll need C2, which is the probability that the second, or is the event that the second criticality 1 system works, and so on. And that's what these little quotes mean. I think this stands for IBID. But I want all of them to work. So if I'm to have a successful mission, so this is part B now, probability of a successful mission really means the probability of C1 and C2 and C3, and well, this is going to get kind of tedious, so let's just go up to and C750. Wow. A lot has to go right. Now here's the probability stuff. How am I going to calculate that probability? What is there that can help me calculate that probability? Does anyone see anything in the statement of the problem that might be useful?
The 750?
Wow, well done. They're independent. So what's that mean for this calculation? What's it mean for this probability?
It means, sorry, I didn't know.
Go ahead.
It means that, like, if C1 fails, that does not impact the chances of C2.
Good. And as far as the implications for this probability, it means I can calculate this as the probability of C1 times the probability of C2 times the probability of C3, all the way down to the probability of C750. Good so far? Someone tell me what that first probability is. Probability that one of these parts fail, or succeeds, I should say. Yeah, 0.9999. And the second one is 0.9999. And so on. And so what I want you to do is I want you to take out your calculator and multiply 0.9999 times itself 750 times. I'm going to go get a cup of coffee. I'll be back. Maybe you'll be done by then. Or I don't know. Maybe. Does anyone know of a shortcut on that? To multiplying this out by itself? Yeah, let's raise it to a power, right? 0.9999 raised to 750 power. Okay. Let's find that number. And round it off to the nearest fourth decimal place. What are you getting? Should be about 0.9277. Okay, so that's the probability of a successful mission. Now, in order to have a successful mission, all 750 parts have to work. Let's look at the probability of a failure. Probability of mission failure. Failure. Well, that's going to mean 1 minus probability of success. Probability of success, well, we just calculated that, 0.9277. So what's that give us for the probability of a mission failure?
Are we turning into a percentage?
I would accept either answer, percentage or decimal. I don't think that there's much sense in quibbling about which one is better. I mean, they're both saying the same thing. So you got about a 7% chance of a mission failure. Wow. That's not really good. That's not what I want to ride up into space, something with a 7% chance of failure. No, it doesn't sound too good at all. Comments. Are you okay with what we did here? We used our complementation rule. There's a lot of ways that you could have a failure. Failure means that at least one of those parts doesn't work. So if you had a little number line here, like we did earlier, then you could put 0, 1, 2, 3, all the way up to 750. Let's let these be the number of working criticality 1 parts. So the number of working, I'm just going to call them criticality 1 parts. So if you have a mission failure, well, let's see. Let's do it the other way. A successful mission means this right here. That's the only way you're going to have a successful mission, is if all 750 parts work. Everything else is a mission failure. If you have even one of these parts, and in the case of the Shuttle Challenger, it was the O-rings failed. So this is a successful mission, and this is not a successful mission. The calculation of this probability would be really tedious, to say the least. But we don't have to do it that way because we use the complementation rule. The short story is, when you see words of at least and at most, start thinking about the complementation rule. Now there's one more part to this. Let's take a look at that last part. Before I do, are we okay with our calculations in B and C? Any follow-up on that? Maybe I went over a little too fast, something?
What's the calculation for the other part?
This one?
Yeah, the failure.
Oh, that would be really tedious, because you'd have to calculate, for this probability, you have to calculate the probability of C0 or C1 or C2. It'd be a real mess. 749. Yeah, I'd be taking out a computer to do that, because you have to calculate the probability that any number of these parts fail, and they can fail in different ways. So that would be a real mess. You definitely want to do it with the complementation rule, because then you only have to calculate one probability, which is this one. Whereas here you'd have to calculate 749 probabilities, actually 750. Which one?
The other side's of the failure.
Other side of the failure, we got it as 1 minus the probability of success. So in order to get success, you have to have all 750 parts working. And so that's what we calculated in part B, is the probability that all 750 were working. And that means this probability multiplied by itself 750 times. That was our probability of success. So let me write that here. P. No, the probability of, see, the complement of this means at least one of the parts fails. And if the way the criticality one part was defined is that if that one part fails, the mission fails. So if any of these parts fail, or more than one fail, then the mission fails. So in order to get success, you have to have, you know, perfect strike on all 750 of these parts. And that didn't happen, unfortunately. Are we better on that one, Nicholas? Okay, all right, good. Let's finish it up then. There's one last little problem that's part of this. So the Space Shuttle program had 135 missions. So this is part D. 135 missions. And there were 2 failures. With 2 failures. So let's take a look at the overall probability of success based on the data after years and years of the shuttle program. Oops. What's that probability of success? So I got an answer of 133. So without looking at anything at all, and I'm not picking on anyone, I just want to kind of make a point here. Probability of, let's say, A is 133. Without even looking at any context, how would I know that this is wrong? Perfect. It's not between 0 and 1. Probabilities have to be between 0 and 1. Something like this would be very easy for me to grade. All right? It's just wrong. Probabilities, that's one thing I'm going to be kind of picky about. Probabilities have to be between 0 and 1. So there was 133 successful missions. There you go, 135. All right.
I'm about to say.
What's wrong?
Never mind. 'Cause did I not? No.
Okay, Now, there's another way we could calculate this, which would be probability of success is, again, 1 minus the probability of failure. What's the probability of failure in this setting?
1 minus 2 over 135.
Yeah, 1 minus 2 over 135, which is 135 over 135 minus 2 over 135. Or in other words, we're getting the same thing again, 133 over 135. In this case, the complementation rule doesn't save you anything. Kind of, if anything, I guess it's a little bit more lengthy, not much, but at least we're getting the same answers. Here we're just using the complementation rule. There was one last little part to this problem, and that is, let's find the odds for a successful flight. So the odds, and by that I mean A to B, for a successful flight. For that, I would direct your attention to that 133 over 135. What does 133 here represent? Your successes. And this is your failures. So give yourself a second, see if you can't figure out the odds for a successful flight. Now, I know you guys are used to thinking this is hashtag, but I'm old school, all right, so it also means number. Jackson, what would those odds look like, please? Well, it's the number of ways to succeed against the number of ways to fail. How many ways were there to fail in this experiment? Yeah, 133 to 2. So about 67.5 to 1 compared to the nearly 100,000 to 1 that NASA management was saying. So the engineers were certainly a lot more close in their estimates. All right, so a lot of things we covered here. We looked at some odds, probabilities, etc. One last chance here. Anything on this one that you're still curious about, not really comfortable with? Edmund.
So when the question says odds, it's looking for a ratio of
Yes.
what's the amount of time something will succeed versus the amount of time something will fail, where those numbers are both taken from the amount of times you tried.
Right.
And then probability is a percentage.
Probability is, well, it's this thing up here. It's,
The p-value.
yeah.
It has to be 0.
So you're not using the total when you're talking about the probability or the odds, right? We didn't use the 135, we used the 133. So it's the number of successes, not the total number of flights. So that was a little bit different. For our probability, the probability was 133 over 135. So here you're using the total. Here it's just the number of ways you can succeed versus the number of ways you can fail. We could also turn this around, the odds against a successful flight. So let's do that. Odds.
Why did you then do the 133 over 133 plus 2?
Oh, I just split that up.
Oh, you were just drawing it out.
I was just splitting it up so that we could look at it as being our successes and failures, but that total is your 135.
Okay, I see.
So,
I understand that.
yeah, I appreciate that. What do you think the odds against a successful flight would be?
Wouldn't it be flipped?
Yeah, it'd be exactly flipped. Thanks, Lisa. So the odds against a successful flight would be 2 to 133. Okay. And then from there, if you wanted to, you could recombine these and figure out probabilities, etc. But for my money, breaking this up into two little pieces like this helps out a lot when you're considering the odds. And I would suggest that. All right, good questions. Any other follow-up or things on this one? All right, let's flip it over to the back side. Keep working. Among 8,834 cases of pacemaker malfunctions, 504 were found to be caused by firmware. If the firmware is tested in 3 different pacemakers, randomly selected from this batch of 8,834, and the entire batch is accepted if there are no failures, what's the probability that the firmware in the entire batch will be accepted? So, okay, let's figure that one out. There's a lot to unravel here. I'm going to go through it slowly, and then I'll give you a chance to help me work out the next one. But I'm going to let F1 be the event that that the first randomly selected pacemaker has working firmware. The event that the first randomly selected pacemaker has working firmware. So overall, what we're looking for is the probability of acceptance. And for us, I would define the probability of acceptance this way. It's a probability that the first one we take out works, and the second we take out works. Oops, not that. And the third one. So F2 and F3 are pretty much the same thing as F1. It's just that it's the second one and the third draw respectively. In this kind of circumstance, do you think you're drawing with replacement or without replacement? What do you think makes sense to do? Without, yeah. Wouldn't really make sense to sample something and put it back in and then perhaps sample it again. I mean, why would you do that? So you're going to take it without replacement. Now, is without replacement lead to dependent or independent events? Which one does that take you to? Independent. No. See, sampling without replacement leads to dependent events. Sampling with replacement leads to independent events. So that leads us to kind of a problem in terms of our calculations. And what we've done a couple times here today so far is we used independence to do this. So from here to here, this step to this step, that was your independence. So maybe I should write that here for us. Use independence. Okay, then maybe I mixed it up, my bad. These are independents. Well, that's this much I gave you in the problem. But here, we're drawing without replacement. Technically, these are dependent events. But there's something that I said that can help us out here. Has anyone got the front of their notes handy? Does anyone see or know of anything that might help us work with this calculation? Let's look back at the start of our notes. Well, it's not this.
The 5%
Oh, the 5% rule. So let's see if we can work this with the 5% rule. Does it satisfy the 5% rule? Well, let's see. Do you think a sample size of n equal 3, is that less than 5% of our population? N equals 3, that's your sample size. Yeah, that's pretty easy. 5% of this is definitely bigger than 3. So because of the 5% rule, we can get away with treating these things as independent. Now, any place that the book can use the 5% rule, they will. And it makes a difference to your calculations. It makes a difference between getting these things right and wrong. So look out for that 5% rule. I'll talk a little bit in a minute about a different way to think about the 5% rule. But because the sample size of n equal 3 is less than 5% of the population, you can treat the sample or treat the events as if they're independent. Treat the events as if they are independent. And that makes a nice difference to your calculation. So how's your calculation going to proceed? Well, probability of F1 and F2 and F3. We can treat this as probability of F1 times probability of F2 times probability of F3. And in fact, we're going to go one a little bit better. We're just going to treat it as the probability of F1 cubed. Because technically these probabilities change if you go to F2 and F3. We're going to treat it as the cube of this one. So let's figure out, well, what's the probability of drawing the first one out and finding that it actually has working firmware. First things first, what's the denominator? Lizzie? What's the denominator going to be for us in terms of the probability that we get one that's working?
I'm sorry,
I'm trying to find the probability of drawing one out of this experiment that has working firmware. So it's going to be some probability of something over something else. I'm just asking for the denominator.
So it would be the total, it would be 8,834.
8,834. Good. What do I have to do to get the numerator?
Subtract off 504.
Yeah. You got to subtract off the 504. So if you do that over here, 8834 minus 504 is going to give me 8330. So 8330. And we're going to get that a total of 3 times, so we're going to end up cubing it. You know, I'm fine with you just leaving it like that. I don't necessarily need to see a probability there, although I am kind of curious as to what that decimal value would be, because it's hard to look at that and go, oh yeah, that means there's a likelihood or not a likelihood. 83, 84%. So, all right. So that's, I don't know. Do you think that something like this should be shipped if you have 504 of these that are not working? They're pacemakers. I think you want a pretty high probability of finding something like this. So let's see, 504 divided by 8834. There's about a 5.7% chance of getting a bad one. That's a lot of bad ones. I don't think a batch like this should be going through, but if all you're taking is 3 of them, then there's a pretty good chance that they're going to go through. So if you're curious, what the assumption of independence does, if we were to do example C without dependence or without independence, here's what that would look like without independence. Example C without independence. So it would look like probability of F1 and F2 and F3. So the first one wouldn't change. You'd have 8,800 or 8,330 out of 8,834. But after you draw that first one, how many are left in the whole experiment? 8,833. And of those, 8,329 of them are working. And then you draw the second one, 8,328 over 8,832. Is that probability going to be very different than this one? No. So the author says, you know what? In this case, it's good enough to do this. This is the calculation with dependence. This is the calculation with independence. This is what your book's typically going to assume. Let me talk more about the 5% rule here. But let me give you a chance to ask any follow-up on this first. Are we okay with example C? Cosmo? Sam? Okay. All right. So let's look back at the 5% rule. So another way to do the 5% rule, an alternative. If 20 times the sample size is less than your population size, then the sample passes the 5% rule. Sometimes it's easier just to do, 20 times something in your head rather than do 5 times something, 5% times the population size and then compare it at that. So N is your sample size. For instance, in our last one, it's pretty easy to do 20 times 3 in your head. 20 times 3 is 60. Clearly that's less than 8,834. Or in our next one, we have a sample of size 5. Does this pass the 5% rule when our population has a size of 2,875? Well, what's 20 times 5?
100.
100. Is that less than this?
Yeah.
So then it passes the 5% rule. Alternatively, you could do 5% of this. You would get like 143.75. And that's more than 5. But I think 5 times this is a little faster. It's up to you. Let me give you some notation to play with on this one. And I'll let you read it for a second. Incidentally, NOAA is the National Oceanic and Atmospheric Administration, which seems like kind of the wrong agency to be inspecting food, but that's the way it is. So I'm going to let M1 be the event that the randomly selected container meets NOAA's requirements. So I just chose to use the letter M because it's part of meets. And then we want to look at the probability of acceptance. And I would suggest you trying to find acceptance in terms of events M1, M2, etc. So if you're watching this later, then you can fast forward the video until I'm done with my pause. I'm going to give people here a chance to work on this, help each other out. I'll walk around and try and help out as well. Look what we did with the previous one. Try and put a few things together. Test yourself. Are you getting this? See if you can come up with the final answer in terms of a probability. There was a statistically significant spike in deaths in the Pacific Northwest. So they were getting radiation traveling all the way around Europe. It's a long ways. True. But there's something else I said that you might want to keep in mind relative to this one. And we kind of used it in the previous one. Like these technically would be dependent events, but I treated it as if they were independent. Why could I do that? It's not a probability, or it's not a, the probability of an event anymore. That's just a number.
Out of 2,875. So that's true.
Pretty funny.
What do you think? That was in the last one. It was like that too. Because
Don't worry. I
3
think we
out
had
of
the same thing. We did the same thing.
8,834.
Yeah. I think that's right.
It's the same.
All five of them have a cat, all five of them that you can expect that is
And
required.
since this one was just
M1 and M2
to the
and
power
M3
of
all
n,
within 5.
the sample size, and you just have to subtract this from that. And now the teacher does. And I don't even know if this is.
Okay. I was just
It's the
Just
last
buzzing
on
through
the
to try and
paper.
figure out exactly where. Okay, so what does it mean that this batch gets accepted? What has to happen for it to get accepted with all those 5 samples? In words. Yeah. The first one meets the requirements, and the second one meets the requirements, and the third all the way down to the 5th. All right, great. Now we need to calculate this probability, except that could be a little bit tedious if we weren't clever. What clever thing can we do to help ourselves out? I think I started out with this, right? What's 5 times 20? 100. Does this satisfy the 5% rule? Yeah, absolutely. Bless you. So by the 5% rule, I can replace this with a calculation of M1 times M2 and M5, except we're just going to treat this as if they're all exactly the same and calculate it as the probability of the first one passing raised to the 5th power. That's our 5% rule. These are dependent events, if you wanted to be very picky about it, but you know what, we're going to get pretty close to the same probability. So what's the probability that one of these things meets these requirements? Well, how many in this lot are there? And if I take 2,875 and subtract 288, Romina, what do I get?
1,587.
Good, 2,587. So 2,587 raised to the 5th power gives you about 0.58991. Or if I wanted to round that off, 0.5899. Overall, this batch has about a 10% failure rate. Should we have like almost a 60% chance of passing it if it has a 10% failure rate? I would argue no. I don't want to have a 1 in 10 chance of getting something that doesn't meet their requirements, whatever that means. So, in any case, the thing we have to worry about is the calculation. Are we okay with all the steps we took to get this number? One of the big things was using the 5% rule, and your author's pretty good about using it any chance he gets. Use that 5% rule to make this calculation a little bit more manageable. Without that, this calculation would be kind of a pain because you'd have to do 2,587 over 2,875 times 2,586 over 2,874 and keep on going down. It'd be a royal pain. So, anything else on this little review of independence? Evan?
Where did 10% come from?
10% is, if you look at 288 compared to 2,875, this is about 10% of that. So that's what I call the failure rate. That's 10% of this batch isn't passing. And if 10% of my food isn't good, I want a better than 90% chance of getting food that's not going to make me sick.
Okay.
So that's where that 10% is coming from. I just
0.59 means that it's a 0.59 probability or a 50% chance of one of the random 5 we selected, which we extrapolate to take that to the whole. The 288 is 10% of the whole.
yeah. So those two things, the 10% that I was citing really has nothing to do with our probability calculation. I was just noticing that this batch, which has about a 10% failure rate,
Okay, I see.
this batch has a 10% failure rate, and yet it has almost a 60% chance of being passed through as being acceptable. And personally, I would say that, well, something with a 10% failure rate in terms of food is not acceptable. That's all I was saying. So those are separate calculations. Appreciate the clarification. Anything else? All right, let's put this one in the books.